Alright guys, in this playlist I'm going to go through bonding. I think that this playlist is the first big jump from GCSE to A-level. Like, it's the first chapter that you really feel that it's kind of like A-level-y. Okay? So be prepared because it is kind of hard, especially visually. Okay, so the first bit's kind of easy. So we're just going to go through the different types of bonding, just like in GCSE. So the first type we're going to go through is ionic. Okay? And this is a strong electrostatic force of attraction between oppositely charged ions. So, for example, what normally happens is something like sodium. Now I'm just going to draw the outer shell. Sodium has one outer electron, and then something like fluorine has 7. So then these shells, they want to gain a full outer shell, right? So what happens, actually to be honest, it's probably easier if I draw one more shell for sodium. Okay, so I've drawn one more shell for sodium, just so you can understand why I'm doing everything. So essentially these atoms, they want to gain a full outer shell. So to do this, the easiest way for this to happen is if sodium loses this electron here and it goes to this atom here. Okay, so it went from here to here, okay, to the fluorine atom. Then now this is the most outer shell, right? Because there's no electrons here. So this basically just kind of disappears. Okay. And now sodium has a full outer shell because it has 8 electrons. And fluorine has a full outer shell because now it has 8 electrons as well. So they both have full outer shells. However, since sodium lost an electron, it's now got a +1 charge. And since fluorine gained an electron, it now has a -1 charge. Okay? And this +1 and the -1, since they're opposites, they attract each other. And we call this attraction an electrostatic attraction. Okay? So the ionic bond is just the electrostatic force of attraction between the oppositely charged ions. Okay? So it's almost like a magnet, okay? When a south pole and a north pole attract each other, it's kind of like that. And the structure that it forms is called a giant ionic lattice. So it's something like this. And here, basically, you have the oppositely charged ions. So say this one's positive, then this one's going to be negative. So the white ones are all negative and the black ones are all positive. And it just forms a huge ionic lattice of like repeating patterns. And then an example is like sodium chloride or magnesium oxide, or like we did, for example, sodium fluoride. So it's normally between a metal and a non-metal. Okay, a covalent bond is a shared pair of electrons. So if I have 2 non-atoms like fluorine, these look like this. Okay, and both of these have 7 electrons in the outer shell. Now, like we said before, atoms want to gain a full outer shell, right? So the easiest way for these to gain a full outer shell is for each of them to gain an electron. However, if I take an electron from here and then add it here, like I did before, then this only has 6 electrons, and this would have 8, so that this would be full. However, this only has 6, okay, so it's not full. So we can't do that. So what happens is that each of these share an electron. So like this. So this here is the covalent bond, and essentially it's just the pair of electrons. And the reason why this makes the atom gain a full outer shell is that if we count the electrons on this atom here, this fluorine, then we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we have 8 electrons, so this shell is complete. And if we count the electrons here, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that shell's complete now as well. So this electron here comes from this atom, and this electron here comes from this atom. Okay, so notice how I've done one atom in circles or dots and the other one in crosses or X's. It really just helps us understand that here the electrons are coming from two different atoms, and that is what is meant by a shared pair of electrons. So when you have a structure that's covalent, normally the structure is something called simple molecular, and this has intermolecular forces. We're going to focus more on that in a later video, and this is between molecules. Okay, so yeah, we're going to focus, that's a whole nother video. And this is normally within structures like iodine, ice, carbon dioxide, water, and methane. Okay, and another type of covalent structures is macromolecular. Okay, so these are giant molecular structures, something like this. And basically, well, simple molecular is like little molecules like CO2, and they all combine together by something called, well, not combine together, but they're all attracted to each other by intermolecular forces. Whereas macromolecular, it's just the whole structure is one big molecule. Okay, so the first two you probably would have gone through at GCSE. If you don't really understand the difference between simple molecular and macromolecular, don't worry about that too much for now. We're going to focus on it more in a later video. Okay, and lastly we have metallic. Okay, so here we have a strong electrostatic force of attraction between the metal positive ions and the delocalized electrons. So essentially, we probably have something like, well, let's say something like sodium. Okay, so we'd have like 2 atoms of sodium, let's just say, and that looks like this. Okay, and once again, these atoms want to form a full shell, right? So the easiest way for them to gain a full shell is by removing the outer electron. So essentially we just remove this electron and it floats around in the air. And we do the same thing here. It just floats around. And then this shell just basically disappears, right? The outer shell. And now the sodium atoms have a charge of +1, right? Okay, so if we look at this diagram here, these positive particles are our ions that just lost an electron. So in the example we did, we had like sodium. Okay, and they're just in structure, so I'm going to fill all of that out now. And then these negative particles are the electrons that we just lost. Okay, and if you think about it, positive ion and there's negative electrons just floating about. So what's going to happen? They're going to be attracted to each other. So if you think about that concept, and then it's easy to understand the definition: a strong electrostatic force of attraction between the metal positive ions and the delocalized electrons. Delocalized just means it doesn't really belong to an atom, it's just kind of wandering about. Okay, just like we know it is, right? And an example is like magnesium, sodium, basically just all the metals. Okay, now you know all the different types of molecules you can have. You should know all the different types of properties about them. So firstly, just make sure when you're talking about molecules and stuff, you only use the word molecule and intermolecular forces when talking about simple molecular substances, okay? This is a key mistake a lot of people make. Ionic compounds, these have high melting points and boiling points. Okay, and this is because you know that strong oppositely charged attraction, which we call an electrostatic force, that's really hard to break, okay? So just remember, if you have an attraction between something positive and something negative, it's going to have a high melting point and a high boiling point, okay? Because it's really strong. So this attraction here is really strong. They're typically really soluble in water. You don't really need to know why, just remember that they are. Now, when they're solid, they're poor conductors of electricity, and this is because the ions can't move, right? So basically, to carry a charge, the electrons have to be able to move, or the ions, have to be able to move so that they can carry around the charge. However, if you're solid, the ions can't move, so they can't carry around the charge. However, when they're molten, which basically just means like melted, liquid, essentially, when they're molten, they're good conductors of electricity because the ions can move. Okay, most of the time they are solids. Okay, that doesn't mean always, but like at room temperature, normally they're solids, and that's because they have the high melting points. Okay, and remember, so if you're talking about something like sodium chloride, yeah, you're not talking about molecules. If you think about sodium chloride, it's normally like one big molecule, so you wouldn't refer to it as molecules. You would just think of it like a lattice. Okay, you wouldn't use the word molecule. Now, simple molecular structures have low boiling points, and this is because there's weak intermolecular forces between these molecules. Once again, we're going to focus on this more. They're generally not that good at dissolving in water. They're poor at conducting electricity, and this is because when they have no ions or delocalized electrons to carry the charge. So basically, to carry a charge, you have to have a charge yourself, essentially. So you have to either be an electron or an ion. However, covalent compounds don't really have charged particles, so that's why they can't carry around charge. Same thing when they're molten, still no ions or electrons, delocalized electrons to carry around the charge. Normally at room temperature they're gases or liquids, and this relates back to the low melting points. Since they have a low melting point and a low boiling point, they're normally gases and liquids. Now macromolecular have high melting points, and this is because you're not actually... the whole structure is one big molecule, so you're not breaking weak intermolecular forces. You're breaking the big covalent bonds, the strong covalent bonds. Okay? And this takes a lot of energy, and because of that, you're going to need a high temperature to break it. So essentially, it has a high melting point. Normally, they're insoluble in water. Now, generally, they're poor conductors of electricity, and this is because, once again, it's covalent, so it doesn't have any ions or delocalized electrons. However, in one example that you should know, graphite, and also actually graphene, so that's another example. Graphite and graphene both have delocalized electrons that can move, therefore they can carry charges. Since an electron has a charge, so it can carry a charge, so it can conduct electricity. When molten, it's really poor as well at conducting electricity, and normally, because of their high melting points, they're solids. Okay, metals have a high melting point as well, because once again, we have something positive and negative. So we have the positive ions and the negative electrons, and these are attracted to each other, right? So there's a strong electrostatic force. So because of that has a lot of energy, right? So it's really hard to break. So because of that, metals have a high melting point. Now they're insoluble in water. That's just another fact to remember. They're a good conductor of electricity, and this is because they have the delocalized electrons that can move around. Same thing with when they're molten. So even when they're liquid, they're a good conductor of electricity. And normally at room temperature, they're a solid as well. Another thing to know is that they're malleable, which basically just means like fairly easy to like bend and stuff. Okay, and this is because if you picture what metal actually looks like, I'm going to draw a structure right now. So this is somewhat what metals look like. Now I haven't drawn the electrons. The electrons are like floating about somewhere here. But basically, these layers of atoms can slide against each other really easily. However, if we had something like this layer here, it can't slide, okay, because this atom here is blocking it. So generally metals are malleable because all of these atoms are the same size. So if we have something like sodium, all of these are sodium atoms, or ions, sorry. So they can all slide against each other because they're all the same size. Whereas here, if all of these are sodium, then this would be a different ion, okay? So a different element. And because of that, it would have a different size. Because of that, it kind of blocks the other layers from sliding against each other. Okay, this can't really slide against that. Okay, here's a question for you guys to try. Which has a higher melting point and boiling point, and why? Magnesium oxide or sodium chloride? Well, the answer is actually magnesium oxide. And the answer is that because magnesium has a +2 charge and oxygen has a -2 charge. sodium has a +1 charge and chlorine has a -1 charge, right? So because magnesium oxide has greater charges, it has a stronger electrostatic attraction, and because of that, it takes more energy to break the forces, essentially, to break the electrostatic attraction. Okay, so a dative covalent bond is when the shared pair of electrons in the covalent bond come from only one of the bonding atoms. So, for example, in NH4 plus, if I draw that, it's something like this, right? And essentially, in one of these bonds, both of the electrons come from the nitrogen, okay? So, in this bond, so normally in a covalent bond, like here for example, one of the atoms comes from the nitrogen and the other one comes from the hydrogen, right? Whereas in this case, both of the electrons come from the nitrogen, okay? And they're both kind of like donated in the bond towards hydrogen, okay? So in an exam, if you're asked to draw the dative covalent bond, it looks like something like this. So we have the nitrogen atom, and essentially, we're asked here, ammonia molecule donates a pair of electrons to a proton, right? H plus. Well, so ammonia looks like this, NH3. Okay, and it donates a pair of electrons, right? So to a H plus. So a H plus is just like this. Now we know that hydrogen has one electron, right? So if we have a H plus, that means we lose an electron. So now this here has 0 electrons, right? So it makes sense why in a covalent bond, it can't donate an electron, or it can't share an electron, because it has no electrons to give, okay? Whereas nitrogen has 5 electrons normally. If you look at the periodic table, it's in group 5, right? So it's giving off one electron here in this bond. It's giving off an electron here in this bond. And it's giving off an electron here in this bond, right? So it has 2 more electrons to kind of give. So it kind of just shares the electrons. It gives both electrons in the bond, okay? But in your exam, you don't really have to draw the electrons. You can just draw a bond like that. However, you do want to show that it's a dative covalent bond and not a normal covalent bond. And the way you do that is you just draw an arrow from the atom that's giving both electrons towards the atom that's receiving both electrons, okay? And then that's your structure. Typically, what we do is we don't leave the charge on the hydrogen. We draw a box and then we do a charge like that. And that's because now the whole molecule has a positive charge, essentially. Okay, so that's what a dative covalent bond is basically. And essentially, you just apply that same concept to any example of a dative covalent bond.